In this video, we're going to wrap up our discussion of end behavior of rational functions by focusing on the case where the polynomial in the numerator of the rational function has the larger degree, right? Where the degree of the numerator of the rational function is greater than the degree of the denominator. Okay, in that case, then the quotient of their leading terms is going to be a non-constant polynomial, and that non-constant polynomial will have the same end behavior as our rational function. And then there's also a little bit in that fact about if that polynomial is linear, but we'll get to that in a few minutes. Okay, so determine the end behavior of the rational function using limit notation. So I'm just going to dive right in and show you exactly what we're talking about here. What we're going to do is we're going to look at f of x equals 4x squared plus 2x plus 3 over x minus 5. And what we're going to do is we're going to grab the highest degree term in the numerator and in the denominator. And then we're going to take them off to the side, and we're going to use that to analyze our end behavior. So we're going to divide 4x squared by x, and we're going to get 4x. And what we're saying is that the end behavior of f is the same as the end behavior of y equals 4x. But we know what the graph of y equals 4x looks like. It's a line with slope 4 that passes through the origin. So we're going to use that to find the limits of f as x approaches infinity and negative infinity. That's the end behavior of f. So considering what happens as x approaches positive infinity, okay, that's over here on this portion of the graph of y equals 4x. Okay, right there. Okay, as x approaches positive infinity, f of x is also approaching positive infinity. And as x approaches negative infinity, okay, as we move to the left, the graph of y is going down, so I would say that the limit of f is negative infinity. And just like it was in the last unit when we were looking at polynomials, and we were determining their end behavior based on their degree and leading coefficient. All right, here's another one. So let's say we'll just repeat the process. Actually, I'm going to grab this just to be as clear as possible because I do care if it's negative, right, with this one. So I'm going to check the end behavior by looking at the quotient of the leading terms. I don't know why I would have selected 7x cubed when there was an x to the 4 right there. Okay, I'm glad I caught that because I would have had to re-record the video. Okay, but x to the 4 is definitely the high degree term there. So I'm going to take x to the 4 divided by negative x to the 2, and I would get negative x squared. Okay. And we know what the graph of y equals negative x squared looks like. So we're going to look at the end behavior of an even degree polynomial with a negative leading coefficient, and we're going to say that as x approaches infinity or negative infinity, f of x is definitely going to negative infinity because we're seeing both sides of this parabola pointing down. Here's another one I'd like to show you before I let you try this on your own. So this one's kind of already written in factored form. And throughout this class we've seen that factored form and standard forms are they're equivalent, and sometimes one is more useful than the other, but it seems to us mostly we're trying to factor always, right? We're always trying to write something in factored form so we can find its zeros usually. But this is a case where we'd be better off to have it in standard form, but we're not going to need to take it all the way to standard form. So what we're going to do is we're going to think about what would happen if we multiplied out x plus 1 squared and then distributed a negative 2x to the 4th. And I asked in class, and I kind of monitored the responses, and it seemed like people were, pretty with me when I was saying, all right, the x plus 1 squared is going to be x squared plus some other stuff, and then I would distribute in a negative 2x to the 4th over that x squared and other things. And I'd have negative 2x to the 6 plus other terms with lower powers of x. And, this is why, in the last unit we gave you things like that and told you, hey, this is a polynomial, determine the degree and leading coefficient, because we were going to need to be, we were hoping you'd be able to, speed some of these processes up here. And if I was to multiply out the bottom, I'd square x squared plus 1, that would end up with 4 powers of x, and then distribute another power of x with that x minus 3. That would be a total of 5 powers of x. And then the leading coefficient would just be 1 because, there's no other number that would get multiplied in. That 3, well, that would only go with a lower power of x. okay, if you think about it, because the maximum power of x is going to use the x in the x minus 3. Okay, so I've got that. I've got my leading terms. I'm going to block them off. Negative 2x to the 6 and an x to the 5. So I'm considering the quotient of negative 2x to the 6 and x to the 5 because that will help me determine my end behavior of g. Okay, so that's going to be negative 2x. So if I drew the graph, I could see the end behaviors by looking at it as x approaches infinity. G is going to negative infinity. And then as x approaches negative infinity, G is approaching positive infinity. Oh, now let's say I get you something to try on. All right, yeah, here's 3 more. So work these with the video paused and then, check your work against mine. And I'm just going to bring my work in here in, 2 or 3 seconds. All right, there you go. So for each of these rational functions, okay, I got it in a standard form if necessary, right? I'm seeing that in the top right and the bottom left. Didn't actually get it into standard form, but found the degree and leading coefficient of the polynomial at the top and bottom, right? Isolated that, took the quotient of those leading terms to determine something that would help me with my end behavior, and then sketched a graph of that and, made the determination from the sketch of the graph. And so, past this, there's going to be more examples, further on in the book and then also in the homework. But I think y'all, this is going to be an operation that y'all are good at. So that means we need to talk about polynomial long division, which is the other topic for today. And so the result of polynomial long division is helpful in finding equations of slanted asymptotes for the graphs of rational functions. All right, and what I will say about polynomial long division, if you've never done it before, you should probably watch a different video that I might link, somewhere around there on your screen, I hope, if I can get the cards to work right. I'm not going to talk about the how-tos. I'm going to kind of actually assume that you know how to do that and are pretty fluent with it. I'll remind you a couple of things about it. But let's just go in and dive in. I don't know if I finished saying it's useful for helping find slanted asymptotes. And so, we've seen where asymptotes can be horizontal. We've also seen where they can be vertical. They can be slanted as well. And I hope to be able to just justify to you why that's even possible with the polynomial long division. So we're going to find the equation of the slant asymptote to the graph of this rational function. So what we're going to do is we're going to set up for that long division. So I'm going to go over here and I'm going to say x squared plus 6x plus 7. And I'm going to space it out. Okay, that's the number one piece of advice I give people when, when they encounter a long division error. What could I do to make that not happen again? It's you could really space out your work. You could try to work down in a straight line. Those are the two things. The straight line thing is probably more of an issue in elementary and middle where we're long dividing numbers. This one, it's kind of hard to subtract x squared minus x if you know what you're doing at all. And so the way it works is that we're going to take this x right here, the leading term of the divisor, and ask ourselves, what do we need to multiply it by to get the first term that's left in the dividend? Okay, and so what do I multiply x by to get x squared? That's going to be an x. And then what I do is I multiply the x over the x plus 5, and so that would be x squared plus 5x. And then we subtract. Okay, get rid of those. And we subtract down. Okay, so x squared minus x squared is 0. 6x minus 5x is 1x, and then we drop down the plus 7. Okay, then I'm going to ask myself, what do I multiply x by to get x? And it's going to be a plus 1. So then I multiply the 1 over the x plus 5 and copy that down here. 1 times x plus 5 is going to be x plus 5. And I'm going to subtract. And I'm going to have x minus x is 0, and 7 minus 5 is 2. Okay? And now that I have nothing left to drop down, that means this is my remainder. Okay? And I like to write it, rather than putting the remainder in the divisor, up in the top of the, algorithm for long division, I'd rather rewrite y. So I'm going to say y equals, well, I did the long division and I got x plus 1 and then a positive 2 for my remainder, so that's positive 2 over the divisor, that's x plus 5. All right, and so now that I've written it like this, some people might call this like mixed number form. For a writer like this, it makes it much more apparent why I've got a slanted asymptote. Think about this fraction 2 over x plus 5. You might know where I'm going with this, but this is the type of fraction that's got a constant in the numerator and that grows in the denominator as x gets bigger. So as x approaches infinity, or really even for x being, even bigger than 10, right? It would be 2 over 15. That's not a very big number. Y is going to be very, very close to x plus 1. And if, x is 1,000 or 1,000,000, we're just basically right at x plus 1 with just a little bit of error. So this is the type of thing that goes to 0 as x approaches infinity or negative infinity. And just think about putting a really large number in right there for the x. You have a really small number back from the fraction. And so we'd otherwise just have y equals x plus 1. And so that's what we say, is that since that fraction that boxed in green is going to 0, this graph's going to have a slanted asymptote of y equals x plus 1. Okay? And that's all it asks for. Find the equation of the slant asymptote. And so we do that with polynomial long division. And so what's going to happen is, if you're asked to do this, you will long divide the polynomials. You will get hopefully a linear function back, and you need to, right? Okay, otherwise you've done something wrong, and it's not a slanted asymptote, it's like a parabola asymptote. I don't even know if that's a word we can use for that type of behavior, but we need to get a linear and then plus a number, plus or minus a number over the divisor. And then the linear part, that's going to be the slanted asymptote. All right, so now this one says find the equations of all the asymptotes to the graph of this rational function. Okay, well, maybe if it says all, it wants vertical and horizontal and slanted. So I'm going to think horizontal. Well, the degree on top is bigger than the degree on bottom, so we're not going to be seeing any of those horizontal asymptotes. That's for when the degree on bottom is bigger or when the degrees are equal. Okay, if we want to find the vertical asymptotes, we're going to be considering where the denominator is equal to 0. We can't be forgetting about that. So we're going to try to solve this equation by factoring, and that looks to me like x minus 3 times x plus 2. We know that would equal 0 if x was equal to 3 or if x was equal to negative 2. And so those are the equations of my vertical asymptotes. Okay. Now we might also consider slanted asymptotes, and if we see the degree on bottom is 1 less than the degree on top, we are going to have a slanted asymptote. So what am I dividing? I'm dividing 2x cubed plus 3x squared plus 5. Okay, and that's why I put this example in, is because this is missing a term. There's no like x to the first power. So when we're doing long division, we do need to put a placeholder 0 there so we don't, forget and slip up and lose place value. So plus 5. And we're dividing by x squared minus x minus 6. All right, and so we're thinking, what do I multiply x squared by to get 2x to the third? That would be a 2x. I'm going to distribute the 2x over the x squared minus 2x. So it would be negative 2x squared, and 2x times negative 6 is negative 12x. Now, I'm going to subtract all of these things. But I think, if I've got two negatives, what I might do is I might switch the signs of everything and say, all right, 2 minus 2 is 0. 3 plus 2 is going to be 5x squared. And then 0 plus 12 is 12x's. And now I'm going to ask myself, what do I multiply x squared by to get 5x squared? That would be positive 5. And then I multiply that back across the x squared minus x minus 6, and that would be 5x squared minus 5x minus 30. I guess I probably should have brought down that plus 5. Okay, and now I'm going to be subtracting this, so really I'm adding those. And 5 minus 5 is 0, 12 and 5 is 17 x's, you can't even see that, and 5 plus 30 is 35. But if we go back and we look at like what were the equations of the asymptotes themselves, we're going to get that from right here. We don't need to worry about the remainder. So we're just going to say the slant asymptote is going to be y equals 2x plus 5. All right, the last new thing I need to tell you about is the no remainder scenario, like when the remainder comes back 0. So if the polynomial function f is divided by the polynomial function g, then f can be written as f equals g times q plus r, where q is the quotient and r is the remainder. And I'm gonna show you what we mean by that. We just did f divided by g. I think this is a little more logical. When we did that long division, we got the quotient, which was kind of like, ended up being the slanted asymptote both times. Plus, there was some sort of remainder that went over the original divisor, the thing I was dividing by. But what I'm going to do is I'm going to multiply both sides of this equation by g. And that will leave me with f equals g times q plus an r, which that's where we get this from. Now, in the situation where r is 0, like we got no remainder in our long division, that would mean that f could be rewritten as g times q, which means that g is a factor of f, and q is just like whatever we factor it out and we're left over with. Okay, so this is just another way of looking at polynomial long division, but we do need to understand the connection between the no remainder scenario and the being a factor. All right, so the polynomial function f here is given by 2x to the 3 minus 9x to the 2 minus 20x plus 12. Determine whether the statements are true or false. Okay, so the first one is the remainder of f of x over x plus 2 is a non-zero constant. I think this would be a good time for you to try the polynomial long division on your own. Do this with the video paused, because I'm just going to bring in the finished product of the f divided by x plus 2 here in just a couple seconds. All right, there you have it. So that one worked out really nice. I hope you did actually pause the video and work this one on your own, because if you did, it really only took 3 steps and it worked out really nicely, and it looked like it wasn't at first. With negative 13, I had my doubts the first time I worked this problem. Okay, but is a non-zero constant? No, that's false. It's a zero constant. Okay, x plus 2 is a factor of f. That's what we just said. If the remainder is 0, then the divisor is a factor of the dividend. So this has got to be true. And then the quotient of f of x over x plus 2 is a factorable quadratic polynomial. Well, this is the quotient right here. So I'm just going to go do a little bit of investigation. So I've got 2x cubed, negative 13x, and positive 6. I'm looking for two numbers that multiply to 2 times 6 is 12, while adding to negative 13. Yes, I've got that. That's negative 12 and negative 1. Okay, so I could, if I wanted to, split up the middle term. Maybe I will do that. And I just went ahead and factored it all away. So since I was able to factor it, I'm going to say that the quotient of f of x over x plus 3 factors into two linear factors involving only real numbers. And I'll just let you wonder about where I got that particular language from. So I'm going to say, yes, that is definitely true. Whoops. Yeah, but I could use red to say that because the red writing is what caused me to believe that. Now, I will also mention that a person could have made this determination by examining the discriminant of that quadratic and seeing that it was a square number, because it's a little known fact from Algebra 2. I'm not sure I even mentioned it in my class. But if the discriminant is a perfect square, then you are sitting on a factorable quadratic. That's certainly not an essential knowledge for AP Pre-Cal. I'll just put it that way. So we're over here. We're going to determine whether P is a factor of G and determine whether the graph of G over P has a slant asymptote. All right, I think this one would be good for you to do on your own. This video is getting a little long. So work this with the video pause. I'll bring in the answers in a couple seconds. All right, I'm not sure what happened here with these examples. I'm pretty sure that one of these was supposed to be a factor and it was supposed to divide out cleanly. Let me do a little more investigation. Okay, no mistake in my long division. I went and tried to factor it on Wolfram Alpha, and it told me the thing wasn't really factorable. So obviously I copied down g of x wrong, but it still made for a pretty decent problem. There was some bad stuff happened on the right with the polynomial long division, but it really wasn't that bad because I realized pretty quickly once I got 2.5 there, I was gonna have a remainder, right? Like I don't really have any choice but to have a remainder. And so, I know that that means that I'm going to have 3x plus 2.5 plus some other stuff that's going to cause me to have a slant asymptote, so I think that's enough on that example. All right, so find the equation of the slant asymptote using long division. That's one, I'm just going to skip that. We've done that one a few times. This polynomial long division, I'm not sure. There might have been a message in that one. But if you want to practice that, just come in and work with me before school or something, right? Like, I'd be happy to work that problem with you anytime, just not right now. Okay, so combine the rational expressions to find the equation for the end behavior. That's one I definitely want to do with you. So what we're going to do, we're going to combine these with common denominator. So I factor the denominator of the first term, the x squared minus 1. I'm going to factor that because I know I can. And then I say, oh, okay, well, I've got one of the factors. I just need to add any other one, so I need to be multiplying by 1. So I add it on top and bottom. And then I'm going to combine these. So I'll have a 4x to the 4 minus, okay, if I distribute the 2 preemptively, I'd have 2x plus 2 over x plus 1, x minus 1. I think at this point I'm going to put it back because I'm trying to determine the end behavior, right? If I'm trying to find the end behavior of the slanted asymptote, it's going to be useful for me to have it in standard form, not factored form. So, continuing to distribute this, distribute the negative, I'd have 4x to the 4 minus 2x plus 2 all divided by x squared minus 1. Right, so I grab the highest power term, 4x to the 4 and 1x to the 2. And let's say the end behavior is going to be determined by that. So that's 4x to the 4 over x to the 2. That's going to be 4x squared. We know what the graph of y equals 4x squared looks like. It's a parabola that opens up. On both sides, I'm seeing f approaching positive infinity, so I'll just say the limit of f of x as x approaches positive or negative infinity is positive infinity. All right, now here, I like this example. This is one that's going to be coming back to you probably on the homework and the quiz and the test. The function h equals f over g has a slant asymptote y equals 2x plus 3. The function f is given by, so that's the numerator, 6x to the 3 minus 4x plus 20. Find the degree and leading coefficient of g. All right, so if I do, that's what we're saying, is if I do 6x cubed minus 4x plus 20 over g of x, that's going to equal 2x plus 3 plus some sort of remainder over g of x. But we don't really care about the remainder, right? We should be able to figure out, just really based on this, right? Back to really the first thing I told you about, we should be able to figure out what's going on here. Because the end behavior of this expression to the right of the equals is going to be the same as the end behavior of y equals 2x, because it's a first degree polynomial with positive leading coefficient with an attached thing that's going to become closer to 0 as x approaches infinity. So I envision, okay, well, what am I going to, make sure happens down here? Okay, that was not exactly the color I was going for, but it'll do. What needs to go down here? What I always do is I grab the leading term of that polynomial and I'll divide it by the leading polynomial, or leading term of this polynomial, and I'll say, all right, 6x cubed over the leading term of g, well, that's all I need to find the degree and leading coefficient of g, over something, I'll call it u. This is equal to 2x. Okay. So what I could do is I could multiply both sides by u. Or, I mean, if you wanted to solve that one with your eyes, be my guest. If you want to say it's 3x squared, I think, yeah, go ahead. So 2x times u. Then I'll solve for u by dividing both sides by 2x. And that's where I'd get 3 times x squared, yeah. All right, so that means that the degree is going to be 2. and then the lead coefficient is going to be 3. All right, and that's all I've got for you for this video. Makes love at practice. That's going to be a separate video. Thanks for watching.